Dear organizers of the IEEE Sensor 2020 conference, we are a research team from the National University of Defense Technology in China. It is our great honor to be part of the IEEE Sensor 2020. As requested, we recorded this video to share our research. Now, please allow me to introduce the main research results of our group. Magnetoresistance is expected to develop into a high-performance magnetic sensor if the 1F noise, hysteresis, and triaxial orthogonality error can be suppressed. In this work, a comprehensive magnetic flux regulation method, including magnetic field guidance, modulation, and compensation, was presented. Then, a tri-axial tunnel junction magnetoresistance sensor integrated with magnetic field regulation structures was designed and fabricated. The test results show that the comprehensive performance of this magnetoresistance sensor has been greatly improved. As a remarkable success of the spintronics, magnetoresistive sensors can detect ultra-low magnetic field due to the high sensitivity, and have been massively used as reading heads by the advantages of ultra-fast response, small volume, low cost, and low power dissipation. Although it is highly expected that MR sensors will have a great bosom in smart traffic, industrial automation, and individual electronics. However, we must be aware that MR sensors are deeply subjected to large 1F noise, magnetic hysteresis, and low sensitivity to perpendicular field. These issues cause several loss in performance for the applications of weak magnetic field scene. In order to solve these problems, we put forward a series of effective methods. To solve the problem of 1F noise in magnetoresistance sensor, we propose a method of flux modulation, seen in Figure A. MR is located in the air gap, formed by two flux concentrators. A magnetic film is suspended on the air gap and can be driven vertically by a microelectric mechanical resonator, and the modulation film approaches the air gap. The magnetic flux prefers to go through the modulation film, and the gap field drops rapidly. On the contrary, and the modulation film lives apart from the air gap, the gap field restores immediately. When the modulation film goes upward and downward, the gap field varies in magnitude between its maximum and minimum. As a result, the external magnetic field is partly transferred up to the higher frequency where the noise is much lower. The seen field Bm can be given by this. Here, B0 is the external magnetic field, and alpha is the efficiency of flux modulation that indicates the transfer rate of the external magnetic field. Magnetic hysteresis is a common effect in existence of MR sensors. It leads to a confused output on account of the multiplicity of response voltage in one given magnetic field. To reduce the effect of hysteresis, we propose a method of magnetic compensation. It is reasonable that, if being operated in a constant magnetic field by real-time tracking and compensating the external magnetic, MR sensors could be free of magnetic hysteresis in theory. The point is how to produce an equal but inward compensation field with some microcoils deployed near MR components. The compensation field can be generated from a proper current flowing through the coils. In order to improve the orthogonality of triaxial magnetic field, we propose the magnetic field guidance, and shown in the figure below, the field gather, a soft magnetic bar, is seated on the flux concentrator and can turn the perpendicular magnetic flux along the flux concentrator so that the MR components can detect the signals in the air gap involved with the perpendicular magnetic field, defining gamma and the coefficient of the field guidance, where Bz and Bzi respectively denote the flux density of z-direction field and the I-direction field originated from z-direction field. We designed a novel triaxial TMR sensor shown in the figure below with the integration of TMR dyes, OX substrate, hybrid resonant beam, and permanently block. The triaxial sensor has a size of 20 mm, 15 mm, 3.5 mm, and can be divided into 4 sensitive components in function, as seen in figure A. Each TMR die carries a pair of flux concentrators and is respectively mounted on a set of spiral microcoils upon the OX substrate. All 4 microcoils function as compensation field generators. The hybrid resonant beam in figure B is composed of a piezoelectric silicon double-clamped beam, 4 silicon cantilevers, and 4 pieces of Ni-F modulation film. Each piece of modulation film is on the bottom surface of each cantilever beam and is hung above the air gap of flux concentrators, figure D. When the AC voltage is applied to the piezoceramic slits, the double-clamped beam variables vertical together with the modulation film and modulate the mirrored magnetic field at the gap, and shown in figure C. The permanent block is seated on the flux concentrators and suspended above the hybrid resonance beam, serving as the field guider for all 4 sensitive components. By real-time tracking and compensating the external magnetic field, TMR operates in a constant magnetic field near zero. Then the outputs can be expressed as this, where Vi, Si, Ii, and Li are the first-order component amplitude of the output voltage at correlation point, sensitivity of the die idea, compensation current, and inductive coefficient, respectively. I represents the signal channel, a total of 4. Finally is the result and discussion. For TMR sensors, the magnetic field detectivity can be obtained by dividing the noise spectrum by the sensitivity. Figure B presents the noise density spectrums of the prototype with a supplied power of 2.5 V. With modulation, the signal is moved to high frequency. The low frequency detectivity increased by nearly 43 times. Figure C shows the x-axis outputs when the magnetic field increases from negative 0.1 millitesla to 0.1 millitesla, and then decreases to negative 0.1 millitesla. It can be seen that there is no hysteresis, and the calculated nonlinearity is improved to 0.5%. This indicates the magnetic field compensation can effectively restrain hysteresis and improve linearity. Figure D shows the test results and fitting curves of non-orthogonality by fitting of the angles and mirrored values. According to the results in figure D, the calculated theta xz is 0.1 degree, which lower than that of traditional triaxial magnetic sensors with a value of about 0.5 degree. There are the main research results. Welcome to ask questions and share with us. Thank you very much.